This program is brought to you by Stanford University. Please visit us at stanford.edu.
Now, how much people after Michelson-Morley really, there were all kinds of explanations of Michelson-Morley experiment. Ether drift, that the ether was being swept along with the Earth and so forth. Or Lorentz contraction, yeah. I mean, Lorentz contraction, of course, was correct. But the way Lorentz thought about it is things moving relative to the ether somehow got squeezed by the ether. Well, I suppose you could always describe it that way, but it wasn't the right way that Einstein thought about it in the end. So they had these mechanistic descriptions. They had these mechanistic attempts at explanations which were not the real far-reaching principle that Einstein came to. So I don't know how much the Michelson-Morley experiment really shook the foundations, but it certainly was a signal that there was something going on that was different than what they expected. So Michelson-Morley, and does everybody know what the problem with radiation was? The problem with black body radiation?
Ultraviolet catastrophe.
The ultraviolet catastrophe. Well, if not, I'll explain it right now. It was a conflict. It was a conflict between two sets of principles. One principle was the wave theory of light. And the wave theory of light said that light could come, light, electromagnetic radiation, could come in any wavelength, whatever. Each wavelength behaved like a harmonic oscillator. The mathematics of a wave of a given wavelength is just the mathematics of an oscillation. So, and this was understood long before the quantum mechanics of oscillations. It was understood in the late 19th century that the mechanics of light, the mechanics of not just light, any kind of waves, that each wave was basically a harmonic oscillator, each wavelength of wave. That was number one. The other thing that it was in conflict with was the principle of statistical mechanics. According to the principles of statistical mechanics, there's something called the equipartition of energy. That if you have a collection of harmonic oscillators, and it doesn't matter what the frequency of the oscillators are, there are many, many different oscillators with different frequencies. When they come into thermal equilibrium, each one has the same amount of energy. Basically, it said that the energy of an oscillation is equal to Boltzmann's constant times the temperature, quite independently of what the frequency of the oscillator is. All right, so now you have light in a cavity, or electromagnetic radiation in a cavity. And in that cavity, you can have waves bouncing back and forth. You can't have waves which, of course, are longer than the size of the cavity. They won't fit into the cavity. But you can have waves of arbitrary wavelength that will fit into the cavity, very small wavelengths like that just barely fit into the cavity. And every single wavelength corresponds to a harmonic oscillator according to the principles of statistical mechanics. According to the principles of Boltzmann and Maxwell and Gibbs and the other people who invented statistical mechanics, every one of these oscillations should have exactly the same amount of energy. Well, that just means an infinite amount of energy because there's an infinite number of different kinds of waves that can be supported inside the cavity. Well, that's a disaster. If you bring the cavity to thermal equilibrium and it has an infinite number of different kinds of oscillations, each with the same energy, then there's an infinite amount of energy in the cavity, and it would simply melt the cavity or vaporize the cavity or destroy the cavity in one way or another. The result is something was deeply wrong. Now, how wrong, people didn't really know. They thought maybe there was something wrong with the way the atoms emitted radiation. For some reason, they didn't emit very high frequency radiation. Nobody really knew. Planck did not recognize. Planck was not the one who recognized. He did write down E equals h nu. No, he wrote down E equals n times h nu. He did say that energy comes in discrete multiples of a certain constant times the frequency of oscillators, and it comes in multiples of that. He did write that down, but he was not thinking about the radiation in the cavity. His theory was that the oscillators in the walls of the cavity, the things which emitted the radiation, that those things had frequencies which were integer multiples of h nu. Okay? That was his theory, and therefore could only emit radiation of integer multiples of E equals h nu. He didn't have a correct theory of what was going on. He wrote this equation down, but the equation didn't apply to the radiation in the cavity. It applied to the things in the walls, according to Planck. He managed to fit the curves of blackbody radiation correctly. He managed to reproduce the spectrum of blackbody radiation, but by arguments which really didn't make sense. The main thing in the argument is that there was a parameter h in the problem. The way we understand it now is to say you simply can't have in each one of these oscillations, you can't have less than one quantum. Okay? If each oscillator has the same energy, and you take oscillators which have very, very high frequency, then they will have to have less than one quantum. In other words, if E equals kT, and kT is a certain number, temperature, Boltzmann's constant is just a numerical constant. Whatever the temperature is, then there will be frequencies which are so large that this energy is less than one quantum of energy. According to classical physics, no problem. You can have an oscillator with any amount of energy. According to quantum mechanics, you cannot have less than one quantum of worth of energy. Less than one quantum means no quanta. And so Einstein's idea was that the waves inside the cavity were quantized, and all those waves which had frequencies so large or wavelengths so small that h nu exceeded kT, they just wouldn't be there. That was Einstein's idea. They wouldn't be there because you couldn't have less than one photon per for each oscillator. So now at first, of course, people did not believe Einstein that light was composed of particles, that it was composed of discrete quanta. For about 20 years, a little bit less than 20 years, for about 18 years, Einstein was very famous. They all agreed he had done something wonderful when he had said that the radiation inside the cavity had E equals h nu, but yet they didn't believe it. They thought there was going to be some way to wiggle out, and somehow the wave theory of light would wind up being correct. They didn't believe it. They didn't believe it until experiments were done where light shines off atoms, gives the atom a kick, and radiation goes off in other directions. This is the Compton effect of scattering of light by charged particles. And it was discovered that the energies and angles exactly conformed to what you would expect from the scattering of particles. Particles come in, particles go out. And if you use energy and momentum conservation, then you can predict various things about the angles and energy that the radiation goes off in. Those things did not follow just from wave theory. They followed from wave theory supplemented with the idea that the radiation comes in discrete packets. And when those experiments were done, it basically took 18 years for people to buy into the theory of photons. And within weeks, literally within weeks, or maybe it was months, I'm not sure, everybody agreed light is made out of photons. So it was one of these critical things that happens all of a sudden, and you wonder why it took so long, but a certain particular experiment sharply separated the time when people believed in photons until they didn't. By that time, of course, everybody knew that the foundations of classical mechanics were wrong when it came to atoms, but they didn't want to believe that the wave theory of light was wrong. Of course, the wave theory of light was not wrong, it was just sort of incomplete.
Didn't the photoelectric effect show that there are photons?
Yeah, you would think that the photoelectric effect would have been enough, but psychologically it was not enough. Right, exactly. Yeah.
I've got a candidate date of 1915 when Bohr explained the hydrogen atom.
It was 1913.
13.
Yeah.
Using Planck's constant.
Yeah. Yeah. Yeah, when he reproduced the Rydberg constant from Planck, when he reproduced the Rydberg constant, the levels of, that was certainly a very critical time. But that was not enough for them to buy into the photon theory. So the photon theory of light, they didn't buy into yet. They did recognize that something radically different was governing the motion of atoms and electrons in atoms than classical mechanics, and that's absolutely right. I mean, Bohr's explanation of atomic levels was a sharp transition. So there were several sharp transitions, but the whole thing stretched itself out over about 20 years, from 25 years, from 1900, Planck's discovery of the Planck constant, to basically 1926, 27, something like that, with 26, which was Schrodinger, Heisenberg, and a little bit later Dirac putting the elements together. It was Einstein who understood most clearly and said it most forcefully, very early, I'm not sure exactly what year, very early, that whatever's going on, because of this new quantum structure, one had to suppose that nature was fundamentally not deterministic. He was the one who said that the emission of radiation, he realized, was a spontaneous, he spoke about spontaneous emission of photons from atoms and from other things, and he understood that it was not deterministic, that it was essentially probabilistic, and it was he who first said nature is not, he who first said God rolls dice, and it was not Bohr, not Bohr, not Born, anybody else. It was Einstein who said that first. And
I think it's kind of interesting, though, that Bohr and the people who were working with the atom were still working with essentially particles in specific orbits and things like that.
Yes.
And they were trying to jigger it to get the quantum effects.
That's right. So it's not completely clear that they recognize the magnitude of their problem.
And it was really,
Right.
When Heisenberg finally decided something's wrong with the whole thing, junk it, let's try it.
Yeah. But as I said, Einstein had already said the world is not deterministic, and you can never ever know enough to be able to predict the emission of the time of emission of a photon. There's nothing you can do to measure that you can measure enough to know when an atom is going to decay. He also talked about radioactivity the same way. He said there's nothing you can do, no measurement that you can make in the atom. He sensed that. He could tell from what was going on that that physics was fundamentally limited to probabilistic explanations of things.
I'm just wondering, since every observation of a photon involves an electron,
Or some charged particle, some charge.
Isn't it enough that one of those particles is quantized?
It's enough that one of them is quantized to prove that the other is. You really can't couple together classical things to quantum mechanical things. It doesn't make sense. You run into contradictions. Trying to keep part of a theory classical and the rest quantum mechanical. It really does run itself into the ground pretty quickly. So it's enough to know that one is quantum mechanical to know that the other has to be quantum mechanical. Yeah.
Yeah, so why did Einstein never really accept the theory? I mean, he was never really satisfied with quantum mechanics, even though what you just said, right? I mean, he was the one that first said it's...
Well, I don't really know. I don't really know. If I had to guess, I would guess he was very, very uncomfortable with the idea of a probabilistic theory. What does probability mean? You flip a coin 1,000 times. What does it tell you about nature that the probability is 50% heads, 50% tails? Does it tell you anything about nature? Does it tell you that, that it will turn up heads 500 times? No, it doesn't tell you that. Does it tell you 500 times within the margin of error? The margin of error being what, square root of 1,030? No, it doesn't tell you that. Does it tell you that you cannot flip 1,000 heads? No, it doesn't tell you that. What does it tell you? It tells you that it's improbable to flip 1,000 heads. Well, probability is being defined in terms of probability. What ultimately does it say about nature that, that if you flip a coin 1,000 times, that the probability is a heads that it will turn up, the probability is 50% that it will turn up heads? I think the only thing I can think of that makes sense is to say you'd be very, very surprised if you're outside the margin of error. It doesn't happen very often. Why doesn't it happen very often? It could happen very often. It could happen every time. Probability theory doesn't tell you that improbable things don't happen. It just tells you they're improbable. Well, what does improbable mean? It just means they hardly ever happen. Well, what do you mean they hardly ever happen? They could happen every time. Oh, but they're improbable. Doesn't say anything. Just says you'd be surprised. I think Einstein was probably troubled by the idea that the most fundamental principles in physics were dependent on nothing more than what he would be surprised by. That's my guess. I think it's probably true.
The impression that I had gotten was that he realized fairly early that there was this probabilistic thing about quantum mechanics, quantum theory.
Right.
And a lot of people felt that the new quantum theory was fundamental, and he thought that it wasn't because he realized this about the theory.
Say it again?
He realized that he saw the probabilistic nature of the theory as a defect.
Yeah.
And a lot of people thought it was the be-all and end-all fundamental theory because it's at the atomic level, it must be fundamental.
Right. What's peculiar is how naive he was at his attempts to outflank quantum mechanics. That's what's surprising. Not that he was troubled by quantum mechanics. Everybody who grows up in physics becomes troubled by quantum mechanics at some point. What's surprising is how naive his attempts to get around it were. Well, it doesn't matter because it historically didn't go anywhere. Let's get back to the Schrodinger equation. We were studying the Schrodinger equation, and let's really go through it now. And finally, tonight, I think, if we can get to it, we will understand the connection with classical mechanics, why momentum in quantum mechanics, which is one thing, is related to momentum in classical mechanics, which is another thing. Why the Hamiltonian of quantum mechanics is called energy, and so forth. And of course, the answer is because in contexts where things are heavy enough to behave according to approximate classical mechanics, these quantities that have been defined in quantum mechanics behave approximately like the corresponding quantities in classical mechanics. All right? But always keep in mind, quantum mechanics is more fundamental. You don't derive quantum mechanics from classical mechanics. You derive the other way. So that's what we're going to do tonight. But let's come back to the Schrodinger equation. Let me remind you what it is. It says it's the equation which tells you how the state vector changes with time. It contains Planck's constant h bar. And it says that the rate of change of the state vector with respect to time is equal to an operator, a Hermitian observable operator that's called h, When I remember to do so, I put a little hat on top of it to indicate that it's an operator acting on psi. That's called the general, we should call it the general Schrodinger equation. Of course, it's not the exact thing that Schrodinger wrote down. All right. We'll supplement this. I want to make a list of some of the equations that we need. Another equation is that momentum, this says that energy is related to time derivatives with a factor of I h bar. A similar equation, similar looking equation, is that momentum, momentum is an operator. Its whole purpose in life is to act on a state vector. I won't bother writing, well, maybe I will write. Nah, let's not write a state vector for it. Let's just write P, that's equal to minus I h bar d by dx. In other words, the time derivative of the wave function is obtained by the Hamiltonian acting on the wave function. The space derivative of the wave function is related to the momentum operator by the same factor I h bar. The minus sign in there, the fact that there's a minus sign here and no minus sign here, is something of a convention. It just historically evolved that way, that there's a minus sign here and no minus sign here. We could change conventions and put a minus sign there too. We won't, because after all, these are venerable conventions, so we'll stick with them. All right, now, last but not least, we're thinking about a particle moving along a line. It has a Hamiltonian, and here's where we use classical physics to make a guess. Not a derivation, but a guess. Pure guess that the Hamiltonian of classical physics, now so far we don't know any particular relationship between this Hamiltonian and the classical physics Hamiltonian, but that's equal to a free particle to p squared over 2m. The fact that it's proportional to p squared and not p, let's start with that. P is a vector for which, for a particle moving along a line, means that it has either a forward sense or a backward sense. Momentum can go this way or it can go this way. All right? We wouldn't want the energy to depend on whether the momentum is in that direction or in that direction. We expect that the energy of a particle moving to the left with a certain momentum is the same as the energy of a particle moving to the right with the same momentum. And so it makes a lot of sense to say that it's proportional to p squared and not p. If p was here by itself, then the energy would be opposite for positive momentum and negative momentum. The fact that there's a 2m here, well, that's essentially the definition of mass, if you like. Again, you could call it something else. You don't need to call it m, but the fact is that energy is proportional to p squared over 2m. Fairly general fact about ordinary non-relativistic particles. So we make the guess. We'll try it out and see what we learn from it, to suppose that the Hamiltonian of quantum mechanics is also p squared over 2m. But now it's in the sense of operators. The operator h is the operator p hat squared over 2m. And as I said, keep in mind the real derivation goes from this blackboard to this blackboard. And we're going to do that derivation tonight. So let's see what that means. What is the meaning of this equation, and how does it connect together with the other equations above it? The only other thing you need to know is what it means. I wrote down what p is. What does p squared mean? P squared simply means you act twice with the same operator. You act with the operator on a state vector, and then you operate with it again, once followed by the second time. All right, so this is enough for us to now write down the Schrodinger equation for a free particle. Instead of writing the ket vector psi, I will just remember that wave functions psi of x form a vector space. The wave function is in general not just a function of position. It is a function of position. Its square tells you the probability for finding the particle at different locations. But of course, it's also implicitly a function of time. It changes with time. Its dependence on time is logically of a different kind than its dependence on space. The state vector is psi of x, but the state vector changes with time. Okay, so that's the way to think about it. Now, we wouldn't speak, for example, about psi star psi being the probability for different times. That doesn't make any sense. What's the probability that the time is such and such? Well, that doesn't make any sense. But it does make sense to say, what's the probability that the particle is located at a particular position at a certain time? So the dependence on x and t are quite logically quite different. X is an observable. Of course, when I look at my clock, I also observe the time. But what I'm really doing is observing the position of the hands on the clock. Those are positions. Okay, so let's write down the Schrodinger equation now. All we have to do is substitute into the top equation. And we get, what do we get? We get I. Let's pull down. We get I h bar d psi of x and t by dt. That's the left-hand side. The right-hand side, we use h is equal to p squared over 2m. So first of all is a 1 over 2m. And then p acts twice. P is minus I h bar d by dx. So we get minus I h bar d by dx. But we write it twice. Minus I h bar d by dx. Acting on psi of x and t. All right, so what does this mean? The first of all, we can take out the factor of minus I h bar squared. Minus I times minus I is minus 1. So first of all, let's get rid of the i's. That gives us our overall minus sign. There's an h bar squared, so let's take out the h bar squared. Now we have d by dx multiplying the d by dx times psi. D by dx times psi just means, it means nothing but derivative of psi with respect to x. Differentiating it again just gives us the second derivative. So this whole thing becomes nothing but the second derivative with respect to x of psi of x. And that's our Schrodinger equation. That's the Schrodinger equation for a free particle. It's the actual equation that Schrodinger actually wrote down. We could get into why he wrote this down, but let's not. Let's just pursue it and work at it from the other end, and we'll eventually see why he wrote it down. Okay, now let's look for solutions of this equation. Let's look for solutions which have the character of being plane waves. Let's look for wave-like solutions. In other words, let's look for solutions whose x dependence is of the form e to the I p over h bar x. Let's look for solutions of that type. Why p over h bar? Well, I can just describe them that way. P, let's say, y p over h bar. Well, if I differentiate, that's just look for solutions of that form.
Omega maybe? You want omega there maybe?
No, I don't want omega there. Omega multiplies time. Okay, so let's put in omega. Omega has to do with time dependence. Let's put in a factor e to the I omega t. In other words, let's assume that the wave function oscillates with time and oscillates with space. The justification for this will be that there do exist solutions like this. Right? These solutions, if we find them, will at any instant of time be eigenvectors of the momentum operator. Remember, eigenvectors of the momentum operator have the form as wave functions e to the I px over h bar. Those are eigenvectors of the momentum operator. They're the things which minus I h bar d by dx act on to give an eigen. They're eigenvectors. They're eigenvectors of the momentum operator. All right. The time dependence here, well, this tells us that wave functions have time dependence. And I'm guessing now that they oscillate with time. That's an oscillation, typical oscillation. Let's plug this into the Schrodinger equation and see if we can find out what omega is. Omega is the unknown. Of course, there may be no such solution like this. We may find that we run the bus into the ditch, that we can't find solutions like this. But of course, if we couldn't, I wouldn't have written it down. Okay, what happens if we take psi of x and differentiate it with respect to time? Every time we differentiate with respect to time, we pull down a factor of I omega. So the left-hand side is just going to give us an I omega times I h bar times psi itself. Here's psi. All right. When I differentiate with respect to time, it'll give me back the same thing except with an I omega in front of it. So that's just psi of x and t. I omega times I h bar, that's just minus h bar omega. Now let's look on the right-hand side. On the right-hand side, every time I differentiate with respect to x, it pulls down I p over h bar. It gives me a factor of I p over h bar. So let's write it all down, is equal to minus h bar squared over 2m. Incidentally, I could have canceled out a factor of h bar from here so it doesn't appear here and only appears once here. We'll do it in this form. Now, what is the second derivative of psi? The second derivative of psi just contains this factor squared, I p over h bar squared. So that gives me I squared is minus 1. That turns this minus sign into a plus sign. It gives me p squared over h bar squared. And then just psi again. All right, so now let's clean it up a little bit. H bar squared over h bar squared, that cancels. Cancel out the h bars. And we get p squared over 2m times psi. The left-hand side, minus omega times h bar times psi. The right-hand side, p squared over 2m times psi. Cancel out the psi's, and what do we find? We find that the frequency minus omega must equal p squared over 2m. Yes, divided to 2mh, thank you. Now, what we're doing from a mathematical point of view is actually finding the eigenvectors. One way of saying it is we're finding the eigenvalues of the Hamiltonian. Omega, when the we'll come back to it. We'll come back to the eigenvalues of the Hamiltonian. That's what omega basically is, an eigenvalue of the Hamiltonian. But we find that the omegas have to be equal to minus p squared over 2mh bar. Let's now use that to rewrite the wave function. The wave function that we found now has the form psi of x and t. And of course, this is only one of many solutions, is of the form e to the I p over h bar x minus I p squared over 2m h bar t. So it oscillates with x and it oscillates with t. The x oscillation is governed by the momentum itself, and the t oscillation is governed by the momentum. If we forget the h bars, in a little while I'll probably set h bar equal to 1. Notice how h bar comes into these formulas. It always comes in the form of a coordinate. Now a coordinate I can either mean x or t. Think of both x's and t's as being coordinates. It always comes in the form x over h bar or t over h bar. Once you know that, you can set h bar to 1 and recover it later by sticking it back into the equations. X over h bar is the only way in which Planck's constant enters into this wave function, and t over h bar. So every time you see x and every time you see t, put an h bar in the denominator, and that will recover for you the factors of Planck's constant. All right, so this is the simplest solution of the Schrodinger equation for a free particle. It corresponds to a particle of momentum p and energy p squared over 2m. Notice there is another wave function which corresponds to exactly the same energy. What is it? If this is a particle moving to the right, it corresponds to a momentum p, which is positive, then there's another one. If we fix p is some positive number, for example. The energy is p squared over 2m. There are two states, two configurations with the same energy. One has p going that way, the other has p going that way. So there's another wave function we could have written down. I'll write it down side by side with this, which would have had the form e to the minus I p over h bar x. But the time dependence is exactly the same. Why is that? That's because this only depends on p squared. All right? So if I change the sign of p, it doesn't change the sign of p squared, and it's minus I p squared over 2m h bar t. These are two wave functions which both correspond to the same energy, but opposite going momentum. You can add them together with arbitrary coefficients. They will no longer be eigenvectors of the momentum because you're mixing together two momenta, but they will have the same energy. So if you add wave functions like this, the energy of the wave of a combined wave function is still p squared over 2m, 2m, not n, m. But you're mixing two momenta. Depending on the coefficients that you would put these two together with, let's put them together with some coefficients. Let's call this one alpha, and let's call this one beta. All right, what's the probability that the particle is moving to the right? Alpha star alpha. Alpha star alpha is the coefficient of the eigenvector with right moving momentum, and the probability that it's moving to the left is beta star beta. What's the probability that it has energy p squared over 2m? 1. All right, 1. All right, so this is a simple example. What constitutes the special relation? I don't know. Special relationship. That knocked me off balance. All right, now, what's the general solution? This is a special solution of the Schrodinger equation corresponding, or it's a family of special solutions with an alpha and a beta, but they all correspond to the same energy. What is the general solution of the Schrodinger equation? The general solution is sums or integrals of wave functions like this. We can take wave functions of the form e to the I p over h bar x minus I p squared over 2m h bar t. And now we can add them, or better yet, we've added them there, but now we can, better yet, integrate them, dp, and just for reasons of convention, I put in the standard square root of 2 pi here, but you don't need to, times an amplitude psi of p, or psi twiddle of p. Now in this expression here, I don't have to include a left-moving and a right-moving momentum. Since I'm integrating over p, let's say from minus infinity to infinity, there are contributions in here where p is positive and contributions where p is negative. So this wave function, which is a sum, which is a superposition, a quantum superposition of states with different momentum p, very much like any quantum superposition. It's a quantum superposition of states with different momenta, and also in general different energies. It's true, the left moving and the right moving with the same value of p have the same energy, but in general, when I integrate up lots of different momenta, I have states in there of very different energy. So this is a quantum superposition that is not only a superposition of different momenta, but also different energies. What's the probability, for example, that this particle has momentum p? Now, when I say it has momentum p, I really mean the momentum density as a function of p. Because momentum is a continuous variable, we describe it by a momentum density. The probability that the momentum is between p and p plus dp. But what's the probability density for the momentum to be p? Well, that's just psi twiddle of p times psi twiddle star of p. Yes?
I thought the dummy variable of integration was p. And it's
Oh, okay, yes, yes. The dummy variable of integration is p. Good, thank you.
and so what is the, why is,
Oh, this is in the integral.
oh, that's in the integral.
That's in the integral, absolutely.
Oh, okay.
That's in the integral.
What's the parameters of
The parameters of what?
of psi twiddle of p?
The parameters.
What's fixed?
What is fixed?
Exercise x and t. I guess nothing is fixed.
Nothing's fixed.
Yeah. And m.
Yeah, oh, yeah, sure, sure. H bar is fixed, M is fixed, I is fixed, E is fixed, infinity is fixed, pi is fixed, 2 is fixed. Right? But other than that, other than almost everything on the board, nothing is fixed. We're integrating over p, which means we're summing up waves of different wavelength. We're summing up waves of different wavelength, some moving to the right, some moving to the left, and we're summing them up with an amplitude psi of p. Each wave has a time dependence, so we're summing up these things. Each one is oscillating. The different ones, they're oscillating with different frequencies. It's a mess. The whole thing is doing very, very complicated things, but it can all be represented as a superposition of different momentum eigenstates. All right, now I come back to my question. What is the probability density? What's the probability density that the particle has momentum, let's say q. Let's not call it p since p is an integration variable. Probability density p of q. That, of course, is nothing but this amplitude squared. Again, it's the same sort of thing. We're adding up wave functions with different coefficients. So this probability is psi twiddle star of q, psi of q. I've just picked a particular value of momentum. I didn't want to call it p because in this formula p is an integration variable. Did I miss a twiddle? Thank you. Good. All right.
Up there, it's a function of momentum, and down here it's a function of position.
No, it's not a function of position. Oh, I'm sorry. We should. You're thinking of p's and q's in the sense of positions and momenta. No. Q here is a momentum. Yeah, we could just call it p prime or something. Yeah, maybe I should do that. No, I don't have to. I've already established the notation that position is x. And p's and q's both mean momenta here, but it's a fair point. If I use x for position, then I won't use q for position. Good, thank you. All right, so this is the probability that the particle has momentum q. What's the probability that the energy is E? What's the probability that the energy is E? Well, the probability that the energy is E, you get two contributions with the same energy. You first write E equals p squared over 2m. That tells you what p to look for. If I want the probability that the particle has energy E, I look for those pieces of the wave function where the momentum satisfies p squared over 2m equals E. In other words, I look for p squared equals 2me. How many p squared, how many p's are there such that p squared is equal to 2me? 2. Namely, the two possible square roots. The two possible square roots, can this be seen? No, it can't, but believe me, there's a plus or minus sign here. Plus or minus square root of 2me is equal to p. So what I do is I look in this wave function, or in this general wave function here, for the contributions which have a given energy. There will be two of them, and the probability, let's call these p plus minus. P plus minus is plus or minus, I'm going to rewrite it. I'm going to rewrite it so everybody can see it. P plus or minus equals plus or minus, now I forgot what it was. Square root of 2me, right? I think that's it. Yeah. So what I do is I go for the two wave functions in here which have this value of energy, right? And I take the total probability for that value of energy. What's it going to be? It's going to be that probability, let's say probability for a given energy is going to be psi twiddle of p plus star psi twiddle of p plus. That's the probability that the momentum is p plus the probability that the momentum is p minus. Where p plus and p minus are just opposite values of the momentum, one going one way, one going the other way. All right, so that's the Schrodinger equation for a free particle. Probably, but I think by now I may have, where? Yeah, no, not in there. No. Nope. The energy in terms of the momentum does not have an h-bar. Energy in terms of momentum is just the same as in classical physics.
So have we found general solution of...
Yeah, that's the general solution of the Schrodinger.
Integral over the shape function.
Yep, that's it. And psi, of course, can be complex. So it's parametrized by a complex function of p. And that's it. That's all of the solutions. There are no, well, I take that back. There are other solutions, but the other solutions have the property that they either blow up or do something terrible in infinity. They simply blow up at infinity. These are all of the solutions that don't blow up at infinity. In other words, which don't have all of their probability way out at infinity. This is all of them. Yeah, all the relevant solutions.
Does that depend on the assumption you made at the very beginning that that they're separable? That you separate the e to the I omega t and I to p x over h bar? Supposing they weren't separable, would that still be the general solution?
If they weren't separable, this wouldn't be the equation. And if this weren't the equation, this wouldn't be the solution. Let's talk about the case where they're not separable. the case where they're not separable, separable just means the wave function factors. No, it's always separable in the sense that, that there's a function of x which may not be a simple e to the ipx times an oscillation in t. We'll prove that. We'll prove that. I hope we'll prove that. I hope we have time to prove it.
Is there an arbitrary phase?
Arbitrary phase. Yeah, you can put an arbitrary coefficient here, complex or real. Yeah, it will still and in fact, these are the arbitrary coefficients. So this could contain a phase. Okay. And the psi of p can contain a phase which depends on p, absolutely. If it didn't depend on p, it wouldn't be very interesting. A phase that depends on p is interesting. In other words, it affects the probabilities. Okay, let's, we want to come to a more, let's see. Yeah, just a second, let me just see my notes. Yeah. Psi twiddle is the Fourier transform of psi of x at time 0. Supposing you go to time 0. If we go to time 0, this is a good question. Let's pursue it. Let's go to time t equals 0. At time t equals 0, this wave function is just minus infinity to infinity, integral dp over square root of 2 pi, e to the I px, psi twiddle of p. That's equal to psi of x at time equals 0. Let's just call it psi of x. This is the definition of the Fourier transform of psi of x. Right? If we happen to have known, here might be the way we might set up a problem. Supposing we knew that at time t equals 0, the wave function of the particle was psi of x. I don't know how we know. We know that the wave function is psi of x at time t equals 0, and we want to find it at a later time. What do? Well, the first thing we do is we find the Fourier transform psi twiddle of p. Let me remind you how you do that. Let's see, let's put it up here. Psi twiddle of p is equal to the integral from minus infinity to infinity. Now, not integral dp, but integral dx. Integral dx e to the minus I px over square root of 2 pi times psi of x. So if somebody tells us what psi of x is at a certain instant of time, let's say at time t equals 0, we can reconstruct what psi of p is. Remember now the reciprocal relationship between Fourier transform of x and Fourier transform of p. Fourier transforms are reciprocally related in such a way that if psi of x is an integral e to the I px psi twiddle of p, then psi twiddle of p is integral, same kind of integral, except over x with a minus sign up here. This is the reciprocal relationship between between functions and their Fourier transforms. All right? So you first find psi twiddle of p. Once you've found psi twiddle of p, you stick it into this formula, which is basically the same formula, except that it now has time dependence. In other words, and this becomes psi of x and t. This becomes psi of x and t. So you start out at time t equals 0 with some knowledge of the wave function. You compute the Fourier transform. That tells you psi twiddle of p. You then stick it in to this time-dependent formula here. The only time dependence is that for each wave, there's an e to the ip squared over 2m times t. And that gives you the full time dependence of the wave function. Now, the wave function will evolve in a complicated way. the different waves that are in it are oscillating with different time dependencies. So for example, the shape of the wave function will not be preserved. If we start out with some general wave function like that, and we start evolving it, the different Fourier components oscillate with different periods. The result is the whole thing is going to move in a complicated pattern which is not going to preserve its shape. But nevertheless, that's the evolution of the wave function. Once you know this, you can then ask, what's the probability at a later time that the particle is located in some particular place? So the kind of problem we might solve is, by hook or crook, somebody tells us what the initial wave function is. And what we want to find out is not at that instant of time what the probability for its location is. That's easy. That's just psi star of x, psi of x. But we want to find out what the probability will be at a later time. After all this complicated motion has taken place, what's the probability to find the particle at a particular place? We go through this operation, we find psi twiddle of p, we plug it into here. That gives us psi of x and t. We can put this on a computer, calculate psi of x and t, and then psi star of x and t times psi of x and t is the new probability at a later time for locating the particle in different places. That's the logic. That's the logic. That's the way quantum mechanics works. Okay. Any other questions? Yes?
So you can also derive psi twiddle of p and t. You can also evolve the psi twiddle.
Psi twiddle of p and t is really just this combination. You see, if I called all of this, everything here, let's put an e to the minus I, and group this together, right? Then we see that we can combine psi twiddle of p with this factor here, and this just becomes the time-dependent Fourier transform of psi of x and t. Does that answer your question? Good. Right, so another way to say it is that the Fourier transform evolves with time, and it evolves with this phase factor here. But as I said, the important thing is this time dependence of the Fourier transform translates in general into a rather complicated variation of the wave function with time, but you can always find it in this way. Yeah?
If the wave doesn't preserve its shape with time, that's a dispersive wave, and it means the different components propagate at different speeds.
Absolutely. Right, now this is true. Right. Right. The different components do propagate with different speed, for sure. It's not surprising, since the different components correspond to different momenta. In fact, there are several different kinds of speeds, group velocity, phase velocity, and so forth, but I won't do that now, group velocity and phase velocity. Yeah, okay. Remind me to tell you something about the schedule because for this class, because I will be gone for some period, and I don't want you to show up here when I won't be here.
Remind you when?
When I'm off the air. Okay. Now, the next thing we want to do is we want to study the evolution of the expectation values. First of all, we want to study a more complicated kind of Schrodinger equation in which the particle is subjected to forces, in which the particle is moving in the presence of a potential function. That's one thing we're going to want to do, and work out the Schrodinger equation. But the other thing we're going to want to do is, once we've done that, we want to see how wave packets move. A wave packet is simply a concentrated wave of some sort, which moves along with some sort of coherent motion. The center of the wave packet, or the average position of the wave packet, moves in some way, and it had better be that, at least in the appropriate circumstances, that the motion of the wave packet looks pretty much like the corresponding motion of a classical system, of a classical particle. We're going to want to work that out. We'll do that tonight. But before we study the more complicated Schrodinger equation, I want to remind you how you calculate the time evolution of expectation values, because that's what we're going to do. We're going to do it for the Schrodinger equation. So 2 steps.
Question?
Yeah.
Just a quick question. So that equation there for psi of x of t, so that could be for a photon, right?
Well, photons are not non-relativistic particles. This is really the theory of non-relativistic particles. So you wouldn't apply this in this form to a photon. Photons simply don't have energies which are p squared over 2m. In fact, they don't have any m. So you wouldn't apply it in quite this form to a photon. Is that the question? Yeah. Yeah, you would have to the rule is that this is an appropriate description for particles moving much, much slower than the speed of light. Okay, question is whether I should, well, I'm trying to, yeah, okay. Let's put a little variety into this. Let's back off the particle on a line and remind ourselves how we compute the time dependence of expectation values. Then we'll come back to a more complicated version of a particle moving on a line. Let's take some observable. Ah, that's a surprise, red. Let's take an observable, let's call it K, and let's take its average value, its expectation value. There's its expectation value. Right? And let's study its time dependence. This is the closest thing to the corresponding classical evolution of that observable. Right? Its expectation value. To calculate it, and we're imagining some fixed observable. The observable itself is not changing with time. It could be position, it could be momentum, it could be spin, it could be polarization, but we're not changing it with time. What is changing with time is the state vectors. So we use the rule for differentiating products. K is not time dependent, but the 2 psi's here are. And let's write this just in the form bra vector time derivative, the dot indicates time derivative, K psi plus psi k times psi dot. I'm going over stuff which we did last time. Now we use the Schrodinger equation. Let's use the Schrodinger equation over here for psi dot. Psi dot is either plus or minus I h psi. I am now going to set h bar equal to 1. H bar equal to 1 because it'll drive me crazy to keep track of it in these equations. H bar is equal to 1. Does anybody remember whether psi dot is plus I times h psi or minus I times h psi? I don't. Minus I. Psi dot is the same thing as psi k. And now psi dot is, I forgot what I just said. Did I say minus or plus? Minus I. So minus I, this one is minus I hope I'm right, times h times psi. Notice we have k over here and h over here. How about this one over here? This one over here, we have to apply the time evolution to the bra vector. That involves a complex conjugation. The minus I will become a plus I. This becomes I psi h k psi. We have 2 different terms. One of them has hk, the other one has kh. The result is I times the expectation value of the commutator of h with k. Remember what the commutator is? It's hk minus kh. I won't bother putting in the psi's here. I just indicate the expectation value of the commutator of h and k. That's the rule. In fact, let's just write this as the time derivative of the expectation value of k for any state. It doesn't matter what state we choose. That is the way the expectation value will evolve. Now, of course, both sides will depend on what state we're talking about. The relationship between the two is always the same, but the actual magnitude of each of these sides depends on what state we're talking about. All right, this is the rule that we're going to use to try to figure out how things evolve in the Schrodinger, how the motion of a wave packet evolves in time. For example, we could apply this to the position, to x itself, to the position operator, and find out how the average position of a particle changes with time. We could apply it to the momentum and find out how the average momentum of a particle changes with time. So let's put this upstairs and keep it for future reference while we do a couple of other simple things. Evidently, we're going to have to compute commutators. Commutators are the things that we're going to have to compute to see how things evolve with time. So let's study a little bit about commutators in quantum mechanics. Just a few simple things. Oh, incidentally, let's compare this with another equation. The corresponding classical equation is that the time derivative of an observable, we won't put brackets around it now because now it really means the time derivative of some classical quantity. Anybody remember what it's given by? By the Poisson bracket. The Poisson bracket, I can't remember if it's k with h or h with k. I always have trouble with these signs. K with h? Are you sure? Are you absolutely sure? Okay, I'll trust you.
So how come it's reversed?
Well, first of all, there's an I in there, among other things. I doubt that it is reversed. Let me just find my own notes. I have h with k in my notes. We can find out fast enough.
Everybody will send you an email.
That's true, but I'm going to write h with k. Last time I had it the other way around?
Yeah, K with H.
Well, it's one way or the other. Okay, let's figure it out. Okay, let's figure it out. We have some function, let's call it k, since we've already called it k. K of x and p, for example. The time derivative of k of x and p is equal to the derivative of k with respect to x times the derivative of x, just the x dt, let's call it x dot, plus the derivative of k with respect to p times p dot. I don't like this red pen, but I've sort of run out of black pens. No, I haven't. Here's another one. Let's hope it's got something in it. All right, this is true. Now, do you remember Hamilton's equations? Hamilton's equations say that x dot is dh dp. So this is dh dp. And that's correct. It really is dh dp, not minus dh dp. P dot is minus dh dx. This is correct. Now, what is this? This is the Poisson bracket of k with h. You were right, Michael, I think.
Well, I was just reading that.
What did you say? You did that in your head while I was... Oh. k K with H is right. Okay. So you can always go back to the basic principle and figure out what's going on. That's correct. Is it possible that we made a mistake in the quantum mechanics? I can't tell. I'm not sure.
The sign of the IH. Could be the sign of the IH. That choice, the Bloch cat.
Yeah. It could be, and maybe it's right. I don't remember.
Well, that's where that order came from, is that we chose the bra to be a minus I and the ket to be...
And I think that's right with all of the conventions I've used up till now.
Okay.
So it looks like that's the way it is. It's just the way it is.
Change the sign, change it to minus I.
Yeah. There's nothing sacred about the sign of I. I suppose that's the way it is. I'm a little surprised, but nevertheless. Oh, no, I think it's right. I think it's right. I think it's right.
I think that's the right the convention, although it seems weird.
Yeah, I think all the conventions are right. Yeah, it's okay. It's right. All right, so let's consider then the connection between Poisson brackets and commutators. There must be some connection between them. They must somehow be the same thing or almost the same thing. So let's look at various Poisson brackets and various commutators and just see to what extent they're similar to each other, to what extent they're different. In fact, we're not going to bother with the differences. They are sometimes different, but almost in most contexts, they're very similar to each other. Poisson brackets and commutators. So let's start with some function of position. It could be the position itself, and take its Poisson bracket with momentum. The definition of that is df by dx, dp by dp, but that's just one. Let's write it, dp by dp, minus df by dp, dp by dx. This second term is 0 on at least 2 counts. The f by dp. First of all, df by dp is 0. F doesn't depend on p. And second of all, dp by dx p doesn't depend on x. So the second term here is completely 0. The derivative of p with respect to itself is 1. And we find the lovely fact that the Poisson bracket of any function of x with p is just the derivative of f with respect to x. In other words, the operation of, there should be a verb for this, a single verb for it, but the operation of Poisson bracketing with p, Poisson with respect, Poisson f with p gives you df by dx, okay? What about commuting f of x? Let's take f of x now to be a quantum operator. What does it mean? It means f of x is an operator which multiplies a wave function by f of x. It takes any function of x, psi of x, and multiplies it by f of x to give a new wave function. That's the operation quantum mechanically of f of x. Let's figure out what the commutator is of f of x with p. To do that, we just write down f of x. Now, p is minus I h bar. I'm going to keep the h bars in for a minute. Minus, I should have kept the h bars in here also. The h bar here is here.
Okay, if you put a minus I there, that's what's in this book as Ehrenfest's theorem.
You think there's a minus sign? I'm not even going to try.
I'm just saying,
Oh.
you have KH,
Oh.
and it's minus I.
Huh?
It's correct as written,
Oh.
or you can have minus I and K.
Oh, I see. Yeah. Okay, good. Right. Okay, so, and I put the h bar back in because I want to keep track of it. There's no h bar, of course, in classical physics. Classical physics has no h bars. All right, so let's take the commutator of f of x with minus I d by dx. That's what p is, and there's an h bar in there, right? Minus I h bar d by dx. I want the commutator of f of x with this object over here. That means I take f of x times this minus the opposite order. Let's put a bracket around there. Minus I h bar d by dx times f of x. That's the commutator between f of x and the thing inside the bracket, which happens to be p. Now, what do I do with this? How am I going to find out what this is equal to? The way to find out what it's equal to is to apply it to an arbitrary wave function, any wave function. So let's take this and apply it to an arbitrary wave function psi of x and see what we get. That's the way to figure out what an operator does, is apply it to a wave function. Okay, let's see if we can figure it out. Do I have the, yeah, okay. First of all, the first term. The first term gives us f of x. It gives us minus I h bar, that's from here, f of x, and then the derivative of psi with respect to x. All right? D by dx just hits psi of x and differentiates it. So what it does is it multiplies, it first differentiates and then multiplies by f of x. The second term gives me a plus I h bar. Minus times minus is plus, h bar. But now the derivative operation hits the product f of x times psi. First f of x multiplies psi, and then you differentiate. You get two terms. So let's put some great big bracket around this. We get two terms. The first term just differentiates psi, leaving f alone. So that gives you f of x times d psi by dx. That's the first term. The second term differentiates f and leaves psi alone. So that gives me plus df by dx times psi of x. Everything inside the bracket. Okay? That's the operation of this commutator acting on a wave function psi. Now, some terms cancel. Here's d psi by dx times I times minus I h bar f. Here's the same thing with a plus sign. These cancel each other, so we might as well just erase them. I think we've done this kind of manipulation before, but let's do it. This term cancels this term. All we have left is I h bar df by dx. Now the f by dx is just a function of x. It's just a function of x, which we then multiply by psi of x. Here's what we learned. We learned that taking this complicated commutator and applying it to any psi of x is the same thing as multiplying psi of x by I h bar df by dx. We can now write very simply that the commutator is just equal, the commutator as an operator is just equal to multiplication by I h bar df by dx. So now I have a simple formula. The commutator of f with p, let's call it p now, minus p times f has exactly the same action as multiplying by I h bar df by dx. Well, let's just compare that. Poisson bracket, Poisson with p gives us df by dx. Commuting with p gives us I h bar df by dx. We could also do a similar calculation to find out what the commutator of x with a function of p is. This is easy for one reason. Remember, there's this reciprocal relationship between p and x. They come in completely parallel to each other. P and x can be sort of interchanged. They're simply Fourier transforms of each other. And it wouldn't be surprising if this formula just gave way to a similar formula in which we differentiate f of p with respect to p. Here, when we commute f of x with p, we get the f by dx. Here, what you get is I h bar the f of p with respect to p. So Poisson with either x or p differentiates. Poisson with p differentiates with respect to x. Poisson with x differentiates with respect to p. Now let me just see if I have the sign right. I think I do. Yeah, there's an easy way to tell. The easy way to tell is supposing f of x was nothing but x itself. Let's write down what this says if f of x is just x. Then it says that the commutator of x with p is equal to I h bar times dx by dx. That's just 1. So it says commutator of x with p is I h bar. That's what happens if you just say f is equal to x. Then df by dx is 1. Let's suppose that f of p is just p. Then this would also say exactly the same thing. It would say commutator of x with p is I h bar times 1. So I have the sign right. If I had put another sign here, I would have an inconsistency between these two formulas. Commutator of x with p is I h bar. What's the Poisson bracket of x with p? That's 1. We can kind of read off this, the relationship between Poisson brackets and commutators. They appear to be, at least in simple situations, they appear to be essentially the same thing except for a factor of I h bar. We can write this in the form that Poisson bracket is equal to commutator. Now, where does the I h bar go? That's the question. I h bar goes here, I believe. Is that correct? Notice, incidentally, that the commutator, whatever it happens to be, let's say x and p, as an example, x and p, x and p. The commutator is much, much smaller than the Poisson bracket by a factor of Planck's constant. Planck's constant is a terribly small number. Commutators are very small. That's natural because in classical physics, xp minus px, that's 0. Commutators are 0 in the classical limit. In the limit that h bar is equal to 0. Commutators are 0. They're only non-zero when h bar is not equal to 0. Then, so here we see how h bar gets into the commutation relations. Okay, so let's just check a few facts about commutators and Poisson brackets and see that they're pretty parallel to each other. Here's an example. A-B Poisson bracket. What's the relationship between that and, I'm writing equal, but I'm going to change it in a moment, BA? What's the relation? Well, one of them is derivative of A with respect to X, derivative of B with respect to P minus the opposite. The other one is exactly the same thing, except in the opposite order. They're negatives of each other. Poisson brackets have this anti-symmetry that Poisson bracket of A with B is minus the Poisson bracket of B with A. Well, of course, that's also true of commutators. The commutator is AB minus BA. That's obviously minus BA minus AB. Here we have AB with a plus sign. Here we have AB with a plus sign. Okay? So Poisson brackets and commutators share the property of anti-symmetry, it's called, that when you invert the order of the two things which you're either Poissing or commuting, the sign changes. So that's a good sign. They have some algebraic similarity. Let me give you another example, which is a very useful fact when you're trying to either compute quickly commutators or Poisson brackets. Oh, good, an empty blackboard. Supposing you have a product, AB, and you want to take its Poisson bracket with a third thing, C. You can build up a lot of stuff by starting with some simple things and constructing products. Let's work out what that is. That's dAB by dx, but let me work, all right, that's dAB by dx, dc by dp, minus dAB by dp, dc by dx. But now let's work out the derivative of AB. That's A times the x derivative of B plus B times the x derivative of A, all times the derivative of C with respect to P. And this one is minus A dPB plus B dPA all times dC by dx. Now let's group these. Let's find all the terms with A standing out in front of them. We have A times something, dxB dpc. Right? This is derivative of B with respect to x, derivative of C with respect to P. Let's write it in the same notation. Take this one and this one. What does it give you? It gives you A times the Poisson bracket of B with C. Look at it. A times dxB dpc minus A times dpB dxc. That is nothing but A times the Poisson bracket of B with C. Now there's the other term. We've gotten rid of this, and we've gotten rid of this. Now there's the term with B undifferentiated. Two of them, two terms with B undifferentiated. So let's put the B out here. And what does it multiply? It multiplies the x derivative of A times the P derivative of C minus the opposite order. And that's just the Poisson bracket of A with C. It doesn't matter that I put the B on the right here and the A on the left. We're talking about classical physics. Classical physics, the order of multiplication doesn't matter. I just wrote it that way because that's the way it comes out in quantum mechanics. But look what it says. It says if you have AB Poisson with C, it gives you A times B Poisson with C plus B times A Poisson with C. It's a simple rule that will carry you a long ways in calculating Poisson brackets. Let's compare it with commutators. Let's do the corresponding thing. Let's ask, could it be the same for commutators? All right, so let's take AB commuted with C. Same operation except in terms of commutators. This would suggest that it's given by A commutator BC plus commutator AC with B. Is this true or is it not true? Well, it's easy to find out. On the left side, we have ABC minus CAB. AB is a single entity, AB times C minus C times AB. Do I have it right? Yes. That's the commutator. Let's check over here. Here we have A times BC minus CB. That's the commutator of BC. And here we have AC minus CA times B. Let's see what we have. We have ABC. Here we have ABC. Minus CAB. Here we have CAB with a minus sign. And then we have ACB minus ACB, I hope. Did I lose a minus sign? Oh, yes. Minus ACB plus ACB is 0. So in fact, commutators have exactly the same property as Poisson brackets. This tells you, if you only know some very simple Poisson brackets, like just x with p, you can start building up complicated products of x's and p's and commuting them or Poissing them, and you'll get the same answers. You'll get the same answers. So Poisson brackets are the natural analog, commutators are the natural analog of Poisson brackets. The equality is not always absolutely true, and the reason is sometimes you get expressions in quantum mechanics which are in classical mechanics, which are a little bit ambiguous in quantum mechanics. If I do some complicated calculation, and at the end of the day, I get x cubed p, then I don't know whether in quantum mechanics this stands for x cubed p, it might stand for x squared px, it might stand for xp x squared, or it might stand for px cubed. They're different operators in quantum mechanics. So there is some ambiguity that when you calculate a Poisson bracket, you don't always know exactly what it stands for in quantum mechanics. But apart from ambiguities like this, Poisson brackets and commutators are equal to within a factor of I h bar. All right. So that's something that's very useful, and we'll use it. We're getting late, so we're running out of time. But I do want to, first, I'm going to do this quickly now. We're going to write the Schrodinger equation for a particle and a potential, and then we're going to study the classical limit using these principles to find out how the averages of the wave packets move. That's our goal for tonight. Work out, or to write down the Schrodinger equation for a particle moving in a potential. We're not going to do much with it. We're not going to solve it. We're just going to calculate how a wave packet moves in time. All right, the starting point is, as always, I d psi by dt, x and t, is equal to h times psi of x and t. But now h is not just going to be p squared over 2m, but it's going to be p squared over 2m plus some potential energy function, which only depends on x. U of x is the potential energy. It corresponds to a force, which is minus the derivative of u with respect to x. And so we're going to plug that into here. What does the p squared over 2m give us? I've left out h bar, incidentally, and I'm going to keep leaving out h bar for the moment, for the rest of the night. Left out h bar. What did we get before? We got p squared over 2m gave us, I believe, minus 1 over 2m times second derivative with respect to x. Sorry, I'm going to put back the h bars, but let's leave them out for the moment. That's the p squared over 2m term. What does u of x mean? U of x just means multiplication by the function u of x. That's all it means. So the second term here is plus u of x times psi of x. I d psi by dt. This is the Schrodinger equation that Schrodinger actually wrote down. It says the time rate of change of psi is just exactly what it was before, plus an extra term, which is u of x times psi of x. Why is the psi of x here? Why not just u of x? Because u of x is an operator that operates on the state vector. So always there's a state vector in there somewheres, either differentiated or undifferentiated. It's there. This is the Schrodinger equation. Let's put in the h bars again. There's an I h bar here. I think there's an h bar squared here, and no h bar at all here. Okay, that's Schrodinger. That is literally the Schrodinger equation that Schrodinger wrote down. Yeah. P is not a function of t. It's just a different. It's an operation. The average of p is a function of time. The average of p is a function of time, and that's what we're going to calculate. P itself is just the operator p, I d by dx. It has no explicit time dependence. The fact that momentum changes with time is the fact that its average changes with time. Why does its average change with time? Because psi changes with time, not because p changes with time. So that's what I wanted to, this is the Schrodinger equation, but I'm actually more interested in the form of the Hamiltonian. Here's the form of the Hamiltonian, and I want to compute, I would like to compute how the average of x and p change with time. They change with time because psi changes with time. This is a complicated equation now. A wave packet may come in, it may hit the potential. There's a potential u of x, which let's draw the potential as a dotted line. Might look like this. The wave packet comes in, experiences the fact that there's a potential. Previously, it didn't have any potential. It did whatever it did, which may have been complicated, but now it's even more complicated. It does something because the potential is there, and we would like to find out, on the average, what does it do? On the average, how does the center of this wave packet move? Right? Now, the answer is that if the potential is a very smooth function, if it varies very smoothly on the scale of the oscillations of the wave function, then the center of the wave function moves exactly according to classical physics. But let's see if we can see that. We have the rules for Poisson brackets and commutators. I'll erase off the blackboard here, but of course we all have them memorized. And we have, here's the equation, here's the operative equation that we want to apply, Let's first figure out, what should we do? Let's first figure out how the average of x changes with time. The average of x changes with time. This is dx dt. We don't have to stick in the wave functions now and do the whole thing. We know it's just equal to the expectation value of the commutator of, well, it's I h bar, I over h bar, commutator of h, which is p squared over 2m plus u of x, that's h, with k, and k is just x. Okay. First thing, the commutator of u of x with x is 0. A thing commutes with any function of itself. X and x squared commute, x and x cubed commute, x with sine of x commute, because all they are is multiplication by functions of x, and it doesn't matter which order you multiply them. So the first thing is, in calculating the commutator of the Hamiltonian with x, u doesn't come into it at all. Let's erase it. U commutes completely with x, it's gone. The important thing is the commutator of x with p squared over 2m. Let's write it down. It's I over h bar, 2m in the denominator, and then the commutator of p squared with x. How do we calculate the commutator of p squared with x? We use this trick. Remember the trick. Commutator AB with c is a commutator BC plus BC A. That's the trick we're going to use. So what's the commutator of p squared with x? Just this piece of it here is p, commutator p with x, plus a and b are both p now. A and b are both p. So it's P commutator Px plus commutator Px with P. That's just using for AB, P squared. Well, what's the commutator of P with X? Not quite. Minus IH bar. Minus IH bar. Commutator of X with P is IH bar. Commutator of P with X is minus IH bar. Each one of these commutators here is just minus IH bar, minus IH bar. H bar is just a number, and all of this is just equal to twice minus 2 IH bar times P. Okay, let's group it together.
On your formula above,
Yeah.
the second part, BCA,
Yeah.
maybe that should be ACB.
Yeah, I think so. Well, AB with C is A, yeah. Sorry. A with C times B. Good. Okay. All right, let's group it together and see what we have here. We have I over 2m h bar, and then we have minus 2i. Let's just erase this and put minus 2i h bar p. I times I is minus 1. That cancels this minus over here. The 2 cancels the 2 over here, and the h bars cancel. H bar cancels H bar, 2 cancels 2. I times I is minus 1, and that cancels the minus here. And what's the net result? The result is P over M. Average of P over M. What have I discovered? I've discovered that the average velocity, what is this? This is just the average velocity of the particle, is equal to the average momentum divided by the mass. Okay. Not surprising. Well, is it surprising? Not. Perhaps it's not so surprising, because if it wouldn't have come out this way, we would have said something's wrong with the connection between classical mechanics and quantum mechanics. But it does come out correct that the average velocity is the average momentum divided by the mass, just as we would expect. Now, what about the average, what about the time dependence of the momentum? It's the time dependence of the momentum which is given by F equals ma. Force is time derivative of momentum. That's classical physics. That's the interesting part here. Let's see if we can recover Newton's equations at least as an average. At least as an average. That's what we want to do, is recover Newton's equations. Newton's equation, F equals ma. So let's apply exactly the same rule to the average of momentum, d by dt, and that's given by I over h bar commutator of
P squared over 2m
p squared over 2m
plus u.
Plus u of x with what? P. Okay, this time it's the u of x which is important. P commutes with p squared. That's not there. It's just the commutator of p with u of x. So this whole thing is I over h bar times the commutator of u of x with p. You remember what the commutator of u of x with p is? Poisson with p does what? It differentiates with respect to x. Poisson with p differentiates with respect to x. That was one of the first things we worked out, which is long gone off the blackboard, unfortunately. But commuting with p also differentiates with respect to x. Well, we worked that out. Commuting a function of x with p gives you the derivative of the function of x. And so this all gives us then I over h bar, and then I can't remember, then I think it's plus another I times h bar times du dx, right? H bar cancels h bar, I times I is minus, and what we find out is that the derivative of the momentum is minus the derivative of u with respect to x. There's another word for the derivative of u with respect to x, and it is force. Yeah, it's also the gradient. Force, F. All right, so first of all, we find that the velocity is given by P over m. That's one of the two equations of Newton. Actually, it's definition of momentum. And the other piece of it is that the force is equal to the time derivative of the momentum. That's all the content of Newton's equations. Force is derivative of momentum. It's actually mass times acceleration, since momentum, we've already shown, is m times velocity. This says momentum is m times velocity, and this says force is m times the derivative of the velocity, which is the acceleration. So we see that the identification of minus I d by dx with momentum and I d by dt with Hamiltonian as energy is you can't call it a correct identification. What you can say is that it's an identification which in the classical limit reproduces classical physics. That's the point. Well, the quantum mechanics is more fundamental, and you derive the classical physics as an approximation for averages. Okay, any questions?
When you did the last semester and you did the Poisson brackets, you had a way where you actually set down a set of postulates. You didn't just use the definition.
Yeah.
And I get two of them where you reverse the ABC rule, and then there was also one where you reversed and showed it's negative, and there's some others. If you do those, are those all analogous?
No.
Would you say that in classical mechanics what you have is a resultant force, whereas in quantum mechanics you don't get a resultant force because you have, the whole thing evolves. The average is a rough equivalent of a resultant force.
What's the resultant force? Result has
Net
to do
force.
with adding vectors.
Well, when you take the gradient of a function, obviously it has vectors pointing in other directions.
Well, here we're only doing one dimension at the moment.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.